So let's see how well this works. So one of the things you might want to be able to do is understand the sentiment of a whole paragraph. Is this a positive statement or a negative statement? And so there's a public data set of IMDb reviews, and you want to be able to say, to predict the review score from just the text. And one thing to note about these paragraphs are pretty long, right? In contrast to other kind of sentence level things, these are pretty long bits of text. And there's a whole bunch of techniques you might imagine using to try to predict the sentiment. And the best one prior to this work was the bag of words plus bigrams plus the naive Bayes SVM, a whole bunch of different things. It got 9% error. And paragraph vectors alone gives you 7.5% error on this sentiment prediction task. There's a different sentiment analysis that focuses more on fairly short phrases. Illuminating if overly talky documentary. That's actually kind of hard. Is that a positive or a negative? I guess it's slightly positive. But again, paragraph vectors does better than a bunch of other techniques you might consider trying. OK, there's a really important side note. These paragraph vectors don't have to be paragraphs, right? They could be sentences. They could be whole documents. They could be sequences of actions a user did. So you would compute then a user vector that's incredibly useful at capturing the long-term dependency information you need to predict things a particular user is going to do. It could be information about a product. It could be the sequence of actions people go through when they're interacting with the product, or it could be, the text of the product reviews. Could be, a sequence of reviews about a movie. Could be audio waveforms. There's all kinds of things these things can be. This powerful notion of being able to embed similar things in a very high-dimensional space so that they're nearby is pretty powerful. So here's an example of paragraph vectors trained on Wikipedia articles. So the actual text of Wikipedia articles, no other information. And if you look at the nearest neighbor articles to the article on machine learning, you see those on the right. And those are pretty good. So there's a version using LDA, which is another technique you might use for topic modeling. And they're pretty similar, but there's a bunch of things in the LDA one that are not nearly as sort of on target as the paragraph vectors. We can also visualize a subset of the Wikipedia articles. I think this is 50,000 Wikipedia articles. And we can color them by their Wikipedia category. And these are laid out by an algorithm called t-SNE, which is somewhat similar to PCA, but is trying a little bit harder to preserve local structure and doesn't care as much about preserving long-distance relationships. So what you see is that different topics tend to be fairly localized in this high-dimensional space. So all the articles on music in green here, music, musicians, anything Wikipedia tagged as related to the topic music, are all kind of in one nice little cluster. Sports is a little more spread out because there's lots of different kinds of sports in the world. Films is kind of near music because there's a fair amount of crossover between those two kind of main topics. Actors is kind of in between music and films, a little closer to films. So it sort of makes intuitive sense that these things are in the right place in this two-dimensional representation of the thousand-dimensional space, or many thousand-dimensional space. Here's a few more, and you see these are kind of more sciencey things, and they're pretty far away from the music-y film world. So computer science is kind of near math, and biology is off to the right and is a little more diffuse, and proteins is a fairly close, tight cluster around biology. So that sort of makes sense, right? Looks pretty good. OK. So that's paragraph vectors. Let me switch to talking about these LSTM-based models, and in particular, how they can be used for translation. So for example, we'd like to be able to take some input, cogito-ergo-sum, and build a big vector representation. Similar spirit to the paragraph vectors, but doing it with a recurrent network. And from that big vector, we'd like to capture enough information about the meaning of that input text to be able to emit a corresponding sentence in another language that means the same thing. Right? That's the translation task. Take in a bunch of text, look at it, think about it, start emitting another language. And traditional machine translation systems work by having a lot of kind of hand-tuned machine-learned models for specific pieces of the translation task. So there's like a phrase table that predicts, you know, this phrase means roughly the same thing in this other language. There's an alignment model which tries to align these words in the source sentence with these words in a target sentence. There's a target language model which says these 4-word sequences are more probable than these 4-word sequences. And then there's a bunch of kind of gooey, messy, handwritten code to glue all these models together, right? And that's kind of annoying and unsatisfying. The nice thing about this model is very pure. You just feed in text, and out comes text in another language. OK, so here's the model. Source language, ABC. Target language, WXYZ. So imagine the source language is English. Target language is French. So you feed in the source language one word at a time. Every time step, your model is recurrent. So the hidden state, the representation of this piece of text in this high-dimensional space, is updated every time we see a new word. Eventually, we're going to feed in an end of English token, special end of English token. And at that point, we're just going to start emitting French, one word at a time. So that's the model. It's more than one hidden layer. There's a lot of details in a paper. But the sentence representation we get at the time we hit the end of English token is all we're using as the representation for the meaning of the text. And this was work done by Ilya Sutskever, Oriol Vinyals, and Kwok Lee in our group. And it's going to appear at NIPS, but it's up on archive now. It's pretty cool. So here's an example translation. Here's Google Translate, which at the moment does not use this neural model. It uses kind of a bunch of these handcrafted machine learned models for various pieces of the translation task. Here's a human translation. So this is kind of the ground truth. And here's the output of the neural model. So it's pretty good for that particular example. And it gets basically state-of-the-art results on the WMT translation task. If we, again, do the same thing where we project small bits of text down and the representations for them down into 2 dimensions using PCA, you can see it's done a plausible job of separating some fairly subtle things that a bag of words representation would do pretty badly on, right? So John admires Mary and Mary admires John. Bag of words representation is the same. That's not good for translation or actual understanding, right? But what you see is that the representation built up by this model has actually done a good job of separating these 2 distinct meanings, even though the words are pretty related. Here's one more example. You know, I was given a card by her in the garden versus she was given a card by me in the garden. Or in the garden, I gave her a card. In the garden, she gave me a card. Those are different meanings. And it's really, really good to have them separated by some reasonably large margin in this high-dimensional space. OK. So in conclusion, I'm going to allow a lot of time for questions. So deep neural nets, I hope I've convinced you that they're pretty effective on a pretty broad variety of problems. You know, the combination of using embedding representations for sparse input data really makes them work well in a lot of problems you might not immediately say, oh, wow, that's obviously a thing a neural net would do. By using parallelism, we're able to train very big networks on very large data sets. And that allows us to make more rapid progress on improving the quality of our models, exploring different ideas. These models automatically build these high-level representations you want to do different tasks. You don't have to kind of spend a lot of time hand engineering things you think might be interesting combinations of raw data you have. You just feed in fairly raw features into these models, and they're able to do a good job of determining, was that actually important for what you care about or not. Embeddings make these things possible to work with sparse data, and it's effective in a lot of different domains. You know, I said we're working with about 30 or 40 teams at Google to apply these techniques across kind of the obvious dense things like speech and vision, but also language modeling, user prediction, a variety of other things like that. So I think these kinds of techniques give you a pretty important tool in building the underpinnings of truly intelligent recommendation systems, right? You really need to understand things about a user, about context, about text, about the world. And with that, you can then do a pretty good job of understanding what would be relevant to a user at this point. OK, so there's a list of a few papers there. There's a few more on various websites. This is, again, I want to emphasize joint work with many, many collaborators at Google. And I'll take questions. How are we doing questions? Are we passing a mic?
Yeah, passing a mic.
We're close.
Yeah, the performance of these deep learning methods is very important. And you spoke also briefly about the different approaches to parallelize the learning. Right? In particular, I would be interested in learning a bit more about the data parallelism. Yeah, you presented this asynchronous distributed stochastic gradient descent, right?
Yep.
You just briefly en passant mentioned that it actually works in practice, which is perhaps somewhat surprising. Basically, the question is, do you have any performance guarantees? Can you be sure that the results of the asynchronous distributed method is somewhat similar, perhaps ideally even the same as the result that you would get in a sequential
no. As I said, this sort of approach makes theoreticians uncomfortable, and so it's often very hard to provide those kinds of guarantees, even in a sequential system, right? Like if you process the input data in a slightly different order, even if you're not doing it asynchronously, you may find a different local minimum. So, you know, I think the only thing I can tell you is empirically, we've done lots of experiments. There's a lot more details in this paper, the second one listed here. That has a bunch of comparisons to looking at sequential versions of SGD versus these asynchronous things versus a much bigger batch style method, LBFGS, which is a second order method. And what we found is that the asynchronous method works with pretty large numbers of replicas, is pretty stable and works reasonably well. But there's obviously no guarantees that it's finding the actual minimum or the same minimum. Even if you train the model twice, it's going to be slightly different. But generally, the accuracy is like within epsilon.
And in the suggested case, basically the issue is that the result depends on the order of presenting these 20 examples to the neural network.
Yeah, for example. Or it can depend on, if you randomly initialize the weights at the beginning of the model, it can depend on that as well.
Sure, thanks.
Sure.
Yes, is the topology or the architecture of the network time-consuming?
Right, so the question is, how do we find the topology of these networks? I have a somewhat unsatisfying answer, which is currently, for almost all of our work, we're hand specifying the topologies. We're saying we want 7 layers, we want this kind of number of connections between the different nodes in the layers. And I think that's a pragmatic approach, but ultimately I think it's not the right approach. And the reason is you really want to develop techniques that automatically discover the architecture. So we're specifying the architecture and making lots of adjustments to the weights in the model along those edges that we specify, but we're not introducing new edges automatically. And ultimately, you want to be doing that. You want to recognize, like, wow, these few things in the layer below me seem really correlated. I'd like to add a new neuron that connects to those correlated things and can construct some higher level feature there. That's what your brain does all the time. I read a stat, between the ages of 2 and 4, your brain makes 500,000 new connections per second. And then it spends 4 to 14 pruning half of them back. So clearly, evolving the architecture is going to be a pretty important thing down the road, but we're not currently there. I think it's a pretty interesting research topic to do that. You're the...
You mentioned reinforcement learning and also interaction with the user, which might be multiple steps. And in this case, it's often beneficial to first do exploration and then exploitation. But deep networks, they are just doing exploitation, right? At least how can do exploration before we do exploitation? I'm
going to defer you to a paper called Learning to Play Atari by our colleagues in our Google London office at DeepMind, which is a company that we purchased about a year ago. They've been exploring how to combine reinforcement learning with deep neural networks for the perceptual part of that. One interesting result they have from that, they've been doing lots of interesting things, but this is kind of the nice soundbitey thing that they've been doing, which is they can play old Atari 2600 games from the raw pixels and learn to play them quite well to superhuman level performance. And the way they do that is there aren't that many moves in an Atari system. Like there's 18 moves you can make with the joystick directions and the buttons. And they use a pretty clever combination of reinforcement learning for deciding which actions were useful along the way. And they start out making random actions and then gradually improve that policy with deep neural networks to do computer vision of the raw pixels, to build these high-level representations of, you know, it's not just a bunch of pixels, it's a frog I'm supposed to jump over or jump on or whatever.
If I may follow up, alternatives, they have a system, right? If you play them right, you always win.
If you what?
If you play them right, you always win. There's a pretty fine set of moves that will make you win in an attack game. While in real interaction, this doesn't exist.
Sure. So I'm not arguing that the Atari game thing is a particularly nice controlled scenario for reinforcement learning. I think the real trick is how do you scale that to bigger and more open-ended environments where you have a much broader set of actions available. You don't have quite as strong a reinforcement queue like the score and your lives left, but you really want to be able to operate in these environments.
So explainability is also a desirable feature of the system, but especially with learning and letting it communicate with the neural net. Is it harder to for conceptual understanding why do you prefer that it's more closely correlated?
Right. So the question is about how explainable are these models? They seem kind of opaque, I think, is the general thrust of the question, which a bunch of people within Google have this same view that these models, while they perform well, are harder to understand than perhaps simpler models or more handcrafted models. And I think that's a valid point of debate. And the question of which side of that debate you come on kind of depends on how much you value explainability versus like an opaque thing that performs better. And I think there's a lot of lessons we can take in how to build tools that allow us to really do introspection on these models and understand better what they're doing. We've done some of that for some of the kinds of models because we want to understand them ourselves so that we can understand the kinds of mistakes they make and understand what research avenues might be promising. But fundamentally, you need to figure out what explainability tools you need, and then it's pretty plausible to build them. I think if you look at the field of neuroscience, as they've gotten better at building explainable models from the measurements they're able to take in nervous systems, that's been pretty useful. And in a computer, you have no limits on the precision your recording instruments have, right? So you should be able to build really good explainable models from introspecting the system. We just haven't put a lot of effort in it.
Great talk. So I was wondering, most of the deep learning techniques that are focused in classification problem, but me myself as a recommendation researcher, I was wondering if there has been any work in optimizing the ranking objective in deep learning literature. I think that thing.
Yeah, I didn't talk about it too much, but you know, these models work pretty well for classification, as you mentioned, but also for ranking problems. You take in a few examples and learn to rank, is this one better than that one, based on some supervised signal. And they actually work pretty well. There's a bunch of techniques for doing that, especially in very large vocabulary systems. So you might have a billion videos and you want to be able to rank, is this one better than this one? And various training techniques for doing ranking loss essentially are pretty effective at doing a job for ranking problems.
Have you tried it with the classic recommender task of filling the missing value in a matrix? Did you go back and would you win the Netflix challenge now?
I don't know. We haven't really tried. I mean, I think a lot of the work we've done has been focused on sort of the business needs of Google, and I think we're going to start applying these to more and more recommendation tasks within Google, particularly because I think the ability to feed in lots of context information about a user without necessarily knowing, you know, which bits of it will be useful is going to be pretty important. Yeah.
So for any model, the distribution of the data of the test data versus the way
Can you speak a little louder? Yeah, it's on. I just.
So when the distribution or behavior of the test data drifts away from what the model was trained on, we expect some degradation.
Sure.
But, can you share insights on how graceful that degradation is with different models?
Sure. So the question is, how quickly do models degrade as the test data distribution changes from the training data? You know, I think we've found that actually these models are fairly smooth. So in some sense, by representing things in these high-dimensional spaces, as long as you kind of get some new examples in roughly the right part of the space, these models are actually somewhat more stable than maybe more direct counting approaches where you haven't seen this particular token a lot and all of a sudden it's got a big spike in activity. But that being said, you're obviously going to get the best performance if you sort of continuously train these kinds of models. So we have deployed systems where we don't need to retrain very often. The acoustic model for speech, for example, you know, people's speech pattern doesn't change all that often, at least at the low level, parts of words kind of things. But then we have other systems that are trying to predict, you know, how likely will the user be to click on this ad versus this one, where we actually do want to train pretty often. And we kind of train those on a nightly basis, maybe. Not much more than that.
In your introduction, you mentioned that the techniques work well if the network is big enough. Can you give us some idea about how big the networks were in your example?
Sure. There were a lot of different examples in the network. So, I mean, I guess for vision problems, we've been looking at ones that have, you know, a few billions of connections. For the language models, once you get in an embedding space, maybe like hundreds of millions of connections. You know, it kind of depends on how much data you have. If you have a modest-sized data set, you don't need as many parameters. And if you have too many parameters, you'll overfit. So a kind of a good rule of thumb for sparse problems is you want one parameter for every record you have. But remember, a lot of those parameters are in the embedding, so they're accessed very sparsely. I give an example, like Palo Alto Restaurants only accesses, say, 3,000 floats out of your, you know, many billion float embedding parameters.
Can you comment on the performance of paragraph vectors compared to neural nets? Because for some of the tasks, you can essentially achieve the same thing with neural nets, right? Where you can learn the word embedding, you can also do classification using
Sure.
current neural nets. So how does this compare to paragraph vectors?
So I think one of the comparisons in the paragraph vector paper was to an RNN of some flavor, I believe. In any case, yeah, I don't think we necessarily did that exact comparison in the paragraph vector work. But I would look in the paragraph vector paper and see if it has comparisons.
Yeah, and since it's not in flavor, I
okay.
So
yeah.
I wonder, what's your perspective on the two models?
My sense is that the paragraph vector model is going to be better at capturing kind of the background topic model of certain kinds of information, and it seems very good at that. But it's perhaps the case that a really big, deep LSTM may be better at capturing the sequential dependencies in sort of detailed understanding of text. That would be my sense, but don't. Obviously, for a particular problem, you want to do your own comparisons.
I would love to know your thoughts around.
Thank you.
Let's say you apply this model and you solve, and things don't work out as well as one would expect. So since it's a fairly new area to begin with, unlike the distributed direction, SNE, ACM, where people have good understanding of the model space, how to debug it, things like that. So what's your thought on how one could interpret or how one could, take further steps if things don't work out as well, say in the first go?
So the question is, how do you actually debug things if something isn't going well or your accuracy isn't as good as you'd hoped? In general, what we do is we kind of try to boil the problem down to a small subset of the problem, like maybe take some subset of the data or a smaller data set and a smaller model so that we can iterate more quickly and try out different things. Sometimes it's a matter of the hyperparameter settings for things like learning rate are not quite right. And we have various parallel techniques for like exploring lots of different configurations for hyperparameters in parallel. Sometimes it's the case that you're just not modeling things right, or there's additional data or kinds of data that would be useful to feed into the model to let it predict things better. It's not a really satisfying answer, but I think it's like lots of machine learning problems in that you just need to poke around a little bit and try to understand why it's not doing what you think it should be doing.
I have a question.
Oh, sorry.
It seems like Google is being worked with Blueprint, and there's an energy-based modeling or deep learning using Boltzmann machines. And then there's another camp that seems not using energy-based models. In your opinion, have you tried those and seen any significant differences? That's one part of the question. Second part of the question is, Google likes the 80-20 rule. So as an engineer, what is the 80-20 rule for minimizing complexity in creating these neural networks versus getting a similar kind of performance?
Okay. The first question was about energy-based models like RBMs versus neural nets. Jeff Hinton sits 5 feet to my left when he's in Mountain View, and we haven't really found kind of the killer app for which RBMs for our production tasks that we care about seem to really be the thing. That doesn't mean that they won't be interesting in the future. We just haven't sort of found something where they're the obvious thing to try and where neural nets are not working well. The second part of the question was about what? Sorry.
Slightly different question, but what's the 80-20 rule?
Oh yeah. Oh sorry. Yes. Now I remember. So simplification and complexity. So I think actually one of the nice properties of neural nets is once you get them working well, they actually form this algorithmically simple computation mechanism. You have this nice black box. It is kind of a black or darkish brown box. But remember, like if you look at the translation example, the current translation system has huge numbers of subsystems and lots of human engineering effort to bring those subsystems together with additional bits of code. And it's very actually complex and very hard to understand. The neural approach the model itself is more opaque, but the actual deployment method would actually be a lot simpler, right? So I think there are different axes of complexity that are important to consider.
So we have time for one very quick question.
How about some in the front, because they've been waiting for a long time.
So you can rephrase it for the
Okay.
camera. But from the very beginning, recommender systems have had ways of incorporating business rules and human expertise for things that may be too rare to learn. So that you're searching for restaurants on Christmas, you want to find restaurants that are actually open on Christmas. You look for Chinese food, or they don't recommend bananas in a supermarket because people buy them anyway. Have you thought about how you might incorporate those types of business rules or human expertise into a model like this that's relatively difficult to manipulate?
Yeah, I mean, I think there's two issues here. One is the sparsity of data. And to that, I think there's ways to augment data that you do have with additional data that you think is predictive of, what you want to have the model do. So for example, you might want to train models for every day of the week or every day of the year that overemphasize that day's data. And that would solve your Christmas problem, probably. We haven't actually tried this, but I suspect that would deal with some of the issues. For other kinds of editorial policies, that's a trickier thing because you're effectively trying to circumvent what the data is telling you to instill some policy on the system. And I think one way to do that is to layer those policy decisions above the model. Essentially, you say, okay, I never want to show banana recommendations in the grocery store, so I do that. Now, it'd be much more satisfying if you had data that would just tell you you shouldn't make banana recommendations. And with enough data, I suspect you might have some way of doing that.
Okay, I think Jeff probably would hang around for a little while
Sure.
in case the questions. So let's give thank Jeff.
Okay, thank you.